Welcome everybody to this new week of Information Systems for Engineers. Today we are going to finish what we started on indices. We are going to look at hash indices and B+3 indices. If time permits, because we are a bit ahead of time, which is great, we might start looking at data cubes, which is a whole completely different shapes than tables. Before we start, though, we are going to take some time for the course evaluation as requested by ETH. So we're going to take 15 minutes for you to fill the questionnaire that you should have received, and on Zoom, people on Zoom as well. So first, could you confirm you received an email by ETH? You did. Okay, awesome. So I'm going to give you 15 minutes starting now. Please take the time to fill it. Give constructive feedback. You know, we are looking for it because we keep improving the lecture. Every year I modify things and take your feedback into account. So please let us know everything that went well, everything that we can improve, that we could change and so on. All right, so you have 15 minutes to do that. And not just in the lecture hall, but also those of you on Zoom. Please take the time to do it. Thank you. All right, so thank you very much for taking the time to fill the questionnaire. Now we are going to continue with clicker questions, as always. So let me swap my screen. So I'm giving you 4 schedules, as you can see here. And the question is, which ones of these schedules are serializable? So of course, we saw an algorithm, right, that you can put everything in a table. You can add the all the conflicts, read, write, read, and write. But here, these are simple enough that you can also just try to reason on a higher level to find tricks that allow you to say whether or not they are serializable. By doing that, rather than the algorithm, it will help you have a high-level understanding, not just mechanical of just doing the algorithm, but actually to understand what's going on and the true meaning of serializability. Oh, maybe I should start the question because otherwise you cannot enter your answers. There you go. So the ones that cannot be serialized, that are not serializable. There seems to be some majority emerging here. Now there is a second majority emerging at the bottom, I see, with more people joining. Right, let me give you the answer then. Who needs more time? Nobody? Okay, let me tell you. This is the correct answer. Can anybody tell me why the first one is not serializable? So remember that not serializable means that there is a cycle So all you need to do is show me one example of cycle. When we talk about cycle, we mean cycles between the transactions. So here there's two transactions, one Alice, the other Bob. So you need a cycle. There's not many ways to have cycles, right? It's that you have Alice to Bob and Bob to Alice, right? So where do we have a conflict from Alice to Bob here? Yes, maybe the third and the fourth. Yes, this is correct. For the next ones, we'll use the microphone. But here I'm repeating the third and the fourth. Indeed, you have Alice writes A, Bob reads A. So there is a row that goes from Alice writes A to Bob reads A, right? And then, of course, as we said, we then squeeze together all the nodes corresponding to the same transaction. So that gives you an arrow from Alice to Bob. What about Bob to Alice to have our cycle? Where is an example of a row from Bob to Alice? Yes, go ahead. Maybe Mark, we can bring the microphone to. The second one to the third one. Yeah, absolutely. Yeah. So this is right. This is a right conflict indeed. So that gives us Bob to Alice. So you see, this is not serializable because if we had any way of swapping the order of these queries, but without inverting the arrows, then we would either have first Alice, then Bob, or first Bob, then Alice, but this doesn't work because you have constraints that force you to have Alice before Bob, and you have other constraints that force you to have Bob before Alice. So that just doesn't work. This is not serializable. The second one is serializable. Why? Why is the second one serializable? Yes, go ahead.
Already serialized?
Exactly, it's already serialized. Serial would be even more accurate. It's already serial. So if it's serial, then in particular, it's serializable, right? So remember that serializable means that it is possible to convert it to a serial schedule, meaning everything Bob and then everything Alice, right? So here it's already serial, so indeed it is thus serializable. The next one, why is it serializable? What can you swap to make it serial? This is also a straightforward answer here. So you see you have Bob, Bob, Alice, Bob, Alice. So this is a bit intertwined. So how do we disentangle the spaghetti here?
We can change the third and the fourth because read has no conflict, and then
exactly, read is not a conflict. So you can swap Alice reads A, Bob reads A. It doesn't matter in which order that is. So you can swap them. Then you get Bob, 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 Alice, Alice, and this is then serial. So this works. And the final one, why is it serializable? Why can you swap things? There was a little bit of a trap here in this one.
Changing A things, and Alice is always changing B things.
Exactly. So they are all minding their own business basically. So Bob is only looking and writing to A, and Alice is only reading and writing to B. So they don't even interact. So there is never any conflict there because the conflict has to be when it's looking at the same place, where it's writing or reading to the same place. But here they're not reading or writing to the same place. So that means that you can swap things. You even have a choice. You can either do everything Bob and then everything Alice, or you can do everything Alice and then everything Bob. That actually works too, because there's absolutely no constraints at all in your graph. There's not even a singular row anywhere. All right, so who now agrees that the first one is the only one that is not serializable? Okay, perfect. So this is what I wanted to do with you, to just make sure that you understand. Of course, here, I didn't use the notation, typically the transaction. So typically with a person is a subscript of R or W, R for read, W for write. And then we put what is written or read in parentheses, right? But here, for the purpose of the question, to make clear the semantics, I just use plain English, right? But just equivalent. And again, to be clear, because that was a question asked last time, I think after the lecture, I'm very often using people's name for the transactions. In reality, you might have different people doing different transactions, right? So it's a bit of a simplification that we just say Bob, Alice, and so on for the transactions. So what happens with serializability is that a typical database system offers you an interface in SQL that allows you to issue multiple queries, reads and writes, as a transaction, meaning that you start the transaction, then you issue your queries, and then at the end you commit. The commit can either succeed and everything is applied, or it can fail and then everything is said to be rolled back, meaning that you were the only one to see these changes and now it's canceled and nobody will ever see anything that you did. So it's either all or nothing. Something else that is important is that typically a transaction time is very short, right? It's just maybe a couple of seconds or maybe even a couple of milliseconds between when you start and when you commit, right? So this is typical. And yeah, all right. So I think this wraps it up. And now we are going to come back to the indices that we started last time. And we also had an answer on Zoom. Bob writes and Alice writes, which is fine, but then Bob's reads again. Exactly, this is why you got your cycle. Yep. All right, don't hesitate to interrupt me when you see answers on Zoom. All right. So where were we? Last week, we looked at views. Views are a way to give names to intermediate results. Right? Normally, when you do a query, you don't give any name to it, right? You can nest queries in queries, but they don't have any names. Tables have names. When you create a table, you give it a name. You give a schema, you give the columns, and it has a name. Well, for reusability, you can give names to some query results, like here we call it publications by Einstein. And that means that you can access it as if it were a table from anywhere. In the from clause, you can now use that name to access it. So we saw that this is very convenient for reusability in queries. We saw that you can choose to materialize your view, meaning that you actually compute it and store it somewhere. Then it's going to be super fast when you query it because it's already pre-computed. But of course, if the underlying data changes, then you have a problem because what you materialize might be missing some recent updates, so it's not fresh. We say that it's stale, right? So you have to re-trigger a new materialization. Or you can also have views that are not materialized, meaning that every time you try to access the view, it just recomputes everything, right? It re-executes that query every time you put the name of the view in a from clause. Okay, then we saw you can update the views under some conditions. It's not always possible, but updating a view basically means that you apply updates to the underlying tables in such a way that it seems like the view had been updated according to your updates. Okay, these are views. Then we look at indices. Indices are typically what you find at the end of a book with this alphabetical list of words that you can quickly look up in order to find the pages on which that word appears. What we've established last time is that if you don't have that at the end of the book and you're looking for a word in the book, you have no choice but to take the book page by page and just scan through it. This takes a lot of time. We call it linear because you just scan through the book. That's called linear. But we've seen that if you're looking up a word in a dictionary, the old way, right now we have the luxury of having computers and the internet to look up words, but if you look up a word in a paper dictionary, like for example at the exam, you are allowed to have dictionaries. Then of course you don't need to read the entire dictionary to find a word, right? Because you know that it's sorted, they're in an alphabetical list of words. So you can just roughly open it in the middle and then look, are you before or after? Then you can again cut it in half and in half and in half and in half until you find the result. This is called a binary search, right? It turns out that this real world thing also applies to databases, because here, if I don't do anything and I'm looking for in a table for a selection, so I'm filtering by author Albert Einstein, if I don't have any structures like this index at the end of the book, there's nothing I can do but a full scan, linear time. I have to go through the entire table. However, if I slightly modify the table and actually sort things by titles, you see here is alphabetically sorted, then I can use my dictionary lookup trick. I can just cut it in half, just like I did here. I grayed out the second half because M is before O. So it's in the first part, and you cut it in half and in half and in half. And that actually gives you what complexity, what time for the lookup. It's not linear, that we know, because it's not a full scan. Does anybody remember? Yes? Logarithmic, exactly. That's logarithmic. And we see on Zoom that you got it right as well. It is indeed logarithmic. What does it mean? So let me again repeat, because the complexity is something that is very important for computer scientists. We actually spend a lot of time on teaching algorithmic complexity. Linear basically means that if you have, I'm caricaturing, imagine you take 1 second for every row. So if you have 1 row, it's 1 second, 10 rows, 10 seconds, 100 rows, 100 seconds, 1,000,000 rows, 1,000,000 seconds. This is linear. If you drew the line, that would be just a y equals x equation. Logarithmic is different. Logarithmic, again, I'm caricaturing, means you have 1 row takes 1 second. 10 rows take 2 seconds. 100 rows take 3 seconds. 1,000 rows take 4 seconds. 10,000 rows take 5 seconds. It means that when you multiply by 10 the size of the data, it only adds 1 second. It doesn't multiply the second, it adds 1 second. This is what it feels to be logarithmic. What it means is that you're just increasing the exponents, right? When you increase the exponent by 1, you actually multiply. So this is why it's logarithmic. Logarithmic is absolutely great news. I'm super happy about that as a user, and this is exactly why looking up in a dictionary is so fast, because that is logarithmic. So binary search gives you logarithmic. Okay, and you can visualize the binary search by representing the data as a tree like that. This is called a tree structure by computer scientists, just like a genealogy tree if you want. Except that trees in computer science are upside down, right? We have the root of the tree at the top and then the leaves at the bottom. So it's the contrary as the way you find trees in nature, at least most trees. And so you basically start here and then it's either left or right, but here we're looking for M, so it's on the left, then D, that's too much to the left, we need to go to the right, then M, now Ma, M, so Ma is left of M, so mathematical logic, right? So this is how we visualize it. Well, in fact, what we do in databases is that we actually do build exactly that structure. We actually materialize that tree structure. And this is how this is the secret for making queries in relational databases super fast, right? And then we can just, once we found it, directly look it up in the table, because then we have what's called a pointer. You know, a pointer gives you exactly the location in the memory of the machine where you find the data. And it turns out that once you have a pointer, it's instant to actually look it up. With the address, you find it immediately, right? It's like the Swiss Post. Somehow they're able to deliver it in 1 day, no matter where you are. So this is instance. Okay, so we've just built an index. So now what I'm going to do is show you this structure, these indices that you can have. In fact, there's 2 of them that I'd like to show you, 2 different kinds of index structures, the hash indices and the tree indices, more exactly the B+3 indices. I'll start with the hash indices, right? What we've seen here was a tree index, so I'll come back to them in the structure, but I would like to show you a hash index. A hash index is something that allows me to locate a value in a table instantly. It's even better than logarithmic, even better than the dictionary lookup, it's instant. You can grow the size of the data, it's still instant. You can multiply by 1,000, it's still the same time, doesn't even add any second. So this is instant. O of 1, that's how computer scientists would say it. Okay. But what's the secret of that? Because it sounds like magic. How can I look up instantly something in a table? Well, the secret is the hash, which is something coming from cryptography. It's actually also something you have in the Bitcoin blockchain, the notion of hash. So here's what we do. We want to index. So here we have a table. We want to build an index structure so that later we can query very easily the centuries. I'm interested in looking up the centuries here. So what do? I just iterate to build my index structure. I start with the first one. That's 20. And I have this magic function that I call h. It's a magic function. What does it do? It takes pretty much anything and it gives me an integer. How is it computed? Well, that's the secret of what there is inside. You don't really know. It's typically a bunch of addition, multiplication things. And thanks to cryptography, you can actually show that it has desirable properties such as looking random, because you cannot really predict what number is going to be. But it's not random, because if I keep asking for h of 20, h of 20, h of 20, it will always give me the same answer. In that case, turns out to be 0. Right? I don't know why it's 0, it just gives me 0. So since I put this 20 through my hash function, think of it like a mixer in your kitchen. So that gives me 0. So I'm going to put that 20 in that table on the left at position 0. Computer scientists, they love to start at 0 when they count. So the first position is actually 0. So I put my 20 here plus a little pointer that points back to the entry that it came from, right? So I put 20 at position 0 in the table, and I put a little pointer to the original table. So I'm done. That what I just did is I indexed the first row of my table. Next, I'm going to take the second row. Oh, it's 20 again, h of 20. As I said, it's always the same result. That's going to give me 0 again. So it's at the same position. Now I add a second pointer at the same time that points to the second record. Then 19, Amanujan, gives me 4. Again, I have no idea why it's 4. It's some kind of hidden stuff that's happening in my hash function. It just turns out to give me 4 after a bunch of additions, multiplications, and modulos. And 4 is the fifth, because again, I said we start at 0 when we index as computer scientists for some obscure reason. So that gives me the fifth row in there. H of 19 is 4, and I add my pointer, okay? Then minus 4, H gives me 3. Again, I don't know why, that's just what it gives me, 3. So position 3, right? 0, 1, 2, 3, here, 3, and I add my pointer. Then I have minus 6, my magic box with the H gives me a 1, so that's position 1, pointing there. And finally 20, well, I know it's going to be 0 because I already saw 20, so I add a pointer here. Who understood what we've just done? Right? It's an algorithm. The only thing that I didn't tell you is what H is doing. And here you just need to trust the cryptographers, basically. It's just the cryptography people who came up with some formulas that do whatever it needs to do in order to look a bit unpredictable. Okay? If you're lucky, you don't have any collisions, meaning that you're not going to have two different centuries that give you the same position. That's a desirable property of hash functions. Why we like hash functions when they are not going to give you the same results for different values. In practice, of course, it's not like that. You do have collisions and computer scientists know exactly how to solve them. But to keep things simple here, I assume that you don't collide. So you will not have two centuries landing in the same position there, just to keep things simple. Okay, so now I'm done building my index structure. So again, if I come back to my book comparison, this is the actual book, right? And this here is the last pages of the book where I have my list of words with the pages. Of course, it's not a list of words with pages because that's something different. It's a hash index, but this would be what you have at the end of the book, right? We've just built it. Okay. Now comes the query. Because now we have the index, so somebody arrives, the user, and says, okay, select star from scientist where century equals 19. That's a selection query. Turns out that PostgreSQL is actually quite smart. It's figuring it out, hey, wait. Century equals 19, but I have an index on century. We've just built it a few minutes ago. So what are we going to do? We take this 19 value. What do we do with it, with 19? Where do we put it? On Zoom, maybe? Any idea what to do with 19? Somebody answer? 4. So you got 4. How did you get 4? Maybe with the microphone, you can explain your reasoning. How did you get this for?
Table, that's row 4, 0, 1, 2, 3,
Absolutely. 4. But the reason why you tell me that's row 4 is that the table is very small. And as a human, you directly see where it is, right? What if there was a billion of these rows, that the table was absolutely immense and there's like plenty of different centuries and you still have to find this for? How did you compute this for? It's just h, right? It's just a function h. That's the secret. But you're correct. That's exactly the right reasoning. You need to locate at position 4, the 19. It's just the extra step that was missing of using function h. Because that function h, we have it. We still have it. And it's exactly the same function h that we used earlier, right? It's just some computer code that takes whatever and returns an integer. So you're absolutely correct. We get 4. So we can immediately go to the 5th row here, so to a row indexed as 4, and then follow the records and find the row, right? This is how I did it. What's the algorithmic complexity of that? Is it linear? Is it logarithmic? Is it instant? Okay, let's do a poll then. Who thinks it's linear? Meaning that if you multiply the table by 10, you make it 10 times bigger, it's going to take times more time. Doesn't seem very popular. Who thinks it's logarithmic? Meaning if you multiply the size of the table by 10, it's adding 1 second. Some of you, who thinks? Yeah, on Zoom?
Somebody said it's instant.
Instant. Who thinks in the lecture hall it's instant? Well, we have a majority. Yes, you're correct. It is instant. To understand that it's instant, you just need to understand that everything here is instant. H is instant. Why? It's just a bunch of plus and multiplies on the number, right? H is instant, gives you instantly the number 4. Looking up here is instant. Why? Because this is stored in my computer memory. And in my computer memory, I have this table here. But in memory, all of that has the same size. So if I'm looking for position 4 here, I can find it instantly. I know it's like in kilometers. Imagine that there's 1 kilometer between 2 rows and I'm here, then I know I need to count exactly 5 kilometers all the way to here. And it turns out that when you look at a computer memory and you know the distance that you have to take to find some bits, it's instant. You can directly jump to the memory. That's why it's called random access memory, RAM, right? Random access memory means it's instant to read where you are. So that step here is also immediate. It's instant. This here is also a pointer. So this is also instant. This might be read from disk, right? But for the disk, it's the same. It's also going to be instant. Maybe an instant that feels a bit longer because reading from this takes more time, but it's still instant in the sense that you can have a billion or a trillion values in there. It's still going to be exactly the same time that it takes. Okay, awesome. So this is instant. So you see, this is absolutely awesome because what did we get here? We have a scheme building an index there that takes time to build. So this is an initial cost. There is a fixed cost of building it, took some time. But now that we have it, anybody can come with a query and we can immediately give an answer to any query, and we can immediately give the answer even if there's a billion or a trillion rows in the table, still immediate answer. Who understands that? Awesome. Then you understand hash indices. And I have super good news for you is that in PostgreSQL, you get that for free. You don't even need to bother about that. Just tell PostgreSQL, please, PostgreSQL, it's like talking to your smartphone, right? Please, PostgreSQL, build me a hash index on that row, and then it's going to take care of it for you. You will not even see that structure anywhere. It's all hidden. What you will see, however, is that when you give your query, the results are instant. Right? Without the index, you might have to wait for an hour, but with the index, it's instant. Okay, is it time for a break? I think I saw it was 50 something. Let me check the time. Yeah, it's 10:59. So I think you deserve the break. Right after the break, I'm going to show you the 3 indices, B+3 indices. And of course, I'm going to tell you why we have them in addition to hash indices, right? Because obviously hash indices have a limitation. that B+3 indices are going to solve. So thank you very much. I'll see you in 15 minutes for the continuation with B+3 indices.